Hi friends, welcome to my channel. Let's have a look at problem 133, clone graph. This is today's daily challenge problem. And in this video, we're going to explain some methods based on traversal. So here we can use both breadth first based or depth first based. And meanwhile, we can use both iterative format and recursive format. So basically, we're going to cover all the cases. First, let's have a look at the problem statement. So here, given a reference of node in a connected undirected graph, so we would like to return a deep copy of the graph. So here are some test cases, right? So basically, in example 1, it demonstrates some right result given in the middle, and the ones that are not the desired ones, like the ones with a cross sign in the above and in the bottom. So here are some further examples. Like in example 2, so this is very special. There's a single node graph, right? And in example 3, so this is the empty one, right? So with that said, let's also have a look at the constraints. So here, the number of nodes in the graph is in the range given by 0 and 100. These are the two ends of the closed interval. And the value can be in between 1 and 100, both ends inclusive. And the node value here is unique for each node. Basically, we can mark each node by its value. And also, there are no repeated edges and no self loops in the graph, right? And the graph is connected, and all nodes can be visited starting from the given node. This actually is an important one. Also, this second to last one, right? So with that said, basically, we are ready to explain our idea or plan. So here, our method or treatments are based on traversal solutions. So the idea is that basically we are going to obtain a mapping or isomorphism. So isomorphism actually is a concept in mathematics. If you have some background in mathematics, like in modern abstract algebra or some other branches, so you will be very familiar with this concept. Here, the key point is that in a standard traversal, one uses a data structure to monitor the nodes that were visited. And here, basically, we're going to use dictionary. So here, it monitors each node visited, and it creates a corresponding node at the same time during the procedure. So this this created one basically establishes a one-one correspondence with the original node. So that's basically what we are going to do in the coding part. So in the previous video, we explained the solutions based on pure iterative format. So we give a challenge that if we can try to use recursion, right? So here we also give the recursion solution format. So here, this is a class signature and initializer signature, right? So node, and then it accepts a value, and it has a neighbors. So the value is a field, and the neighbors is another field. So the neighbor is basically a list, right? So if it's a given, so that's just itself. Otherwise, it's an empty list. We can understand that the neighbors is a list, but it's not specified, right, explicitly, because it can be dark typing, right? So with that said, basically we are ready to write the solution. First, let's look at the iterative format. So here, actually, the solution is based on traversal. It can be BFS or DFS. So here BFS is breadth first based, or breadth first search based, and DFS is depth first search based. So here again we want to mention before we write the code, for doing breadth first search, basically we want to use a queue to monitor the process, and to do depth first search we can use a stack to monitor the procedure. So basically the difference between the queue and the stack are the following. So stack queue is first in, first out, and the stack is first last in, first out. So with that said, we're ready to look at the code. So first I'm going to treat a special case as also edge case. So if not node, right? So basically we are given an empty graph, like in example 3 here, right? So we just need to return, or just let's write a null, none. And then let's do a step 2. So we want to do traversal. So in order to do traversal, we can decide which we want to use. We can use breadth first search or depth first search. So here we are going to use depth first search, and then we are going to comment on breadth first search, right? So here first let's initialize a dictionary, right? So this basically is to, on one hand, to monitor the traversal. On the other hand, we want to have a web correspondence between the original node and its image, or we can say just this actually is playing the same role, or in essence the same as the isomorphism in algebra, right? So now with that said, let's make a container, or let's see container. So let's do not specify the container type, which can be queue or can be stack, depending on how we use it. Then we're going to do this. Visited. Let me first map the node to be another node. So this is an instantiation, right? So we're going to have a value to be the node value, and the neighbors we want to just use default at the very beginning. So then with these preparations, so we can actually do the traversal while container. So what we are going to do first, let's get the node, right? That is container pop, right? So here I'm using it as a stack. So basically we have this one, then we are going to check its neighbor. So for neighbor in the n neighbors, so if neighbor not in visited, so basically what we are going to do, we are going to make the one-man correspondence, right? Visit neighbor is going to be a new node. This is a new instance or object of this node class. So the value will be the neighbor value, right? And the neighbors should be null by default. So basically, for this neighbor, yeah, if we have already made a image, we are going to continue doing the next step. In other words, here. If not, we are going to make this image, right? Then what we are going to do, we want to map the neighbor relation. So the neighbor of the node n should be mapped to visited n. This is the image, its neighbors. We're going to neighbors, right? Neighbors. Then we're going to append, right, this visited neighbor. Notice that neighbor, so that's the NB variable, is a neighbor of this variable n, right, the node. And then visited n, or let's see, visited NB will be the corresponding one of the corresponding neighbors for visited n, right? This is the map relation. So with that done, basically we are done. So now let's do the return. Because we want to return a deep copy, so we are going to return visited node. So that's about it. This is one solution format. Before we move forward or make comments, let's do a check. Here, so we need to return a copy. Let's see. I guess here we forgot to container append this neighbor. So now let's first check, then comment. Yeah, it passes a special case. Now let's look at the generic case. Yeah, it passes all the generic cases. So here, let me comment on the code. So first, let's look at this line here. This pop, and also this append, right? So if we look at this 2 star, right? So basically, we pop from the tail, and then we append from the tail. The tail of the list actually acts as the top of the stack. So basically, we are using this container as a stack. So if we pop from 0 and then we append from the right side, then this actually we use the container as a queue. It also works. This corresponds to breadth first search based, right? And then if you let's test again. If you do pop, this corresponding to depth first search. So here, let me maybe comment here. So pop from the tail and append from the tail. This is actually corresponds to depth first search. And then if we pop 0 and append from the tail, it corresponds to breadth first search based solution, right? So in other words, in this iterative format, we covered both breadth first search and depth first search. So with that said, let me make another comment. So here in this problem, I guess its purpose is not just let us to call the deep copy method, right? If we call the deep copy method, it will just pass, and but I guess that's not what we intended to do, right? So this is the iterative format. Now let's look at another solution. I'm going to copy this part. I'll call this one solution V1, and then here I'm going to write a recursion or recursive format. So basically, we want to use depth first search. For this, actually, if we have already absorbed the above solution, so this will be routine, I guess. So now let me first set a variable called d. So d is a dictionary, so it's corresponding to the visited. So basically, the visited above, right? So basically, its purpose is establish a variant correspondence between the original nodes and the image nodes, right? And then what we are going to do here, I'm going to write a hyperfunction. So let me write a step 1 utility function. So here I'm going to call this function depth first search, and then it accepts a node, right? So you can think of this the original node as this node. And then what we are going to do, so here I'm going to assume this one is not null, right? If it's null, so it's nothing, no point to write this hyperfunction. But we just need to treat the edge case like above here, right? So what we are going to do is to check if the original node is not in D. In other words, we haven't make an image for this D or make a one corresponding node. Then we are going to do this instantiation, right? So we are going to map it to an image node. So the image node, we are going to define it as this. So original value, and we will use default or just specify the neighbors are currently null. Let me just write this. It may be more shorter. So this is the one. So once we established the one-one correspondence, then we're going to check the neighbors. So here we're going to check because the original node has already established the neighbor relations. So here I'm going to check the neighbors of this corresponding image for the original node. So here basically we want to do the same thing in DFS for all the neighbors, right? Basically what we are going to do, basically we make a map. So we map this function to the neighbors of the original nodes, right? So then what we're going to do, so basically because due to the signature here, it's a list. I'm going to make a list convert it to a list, right? So this is going to give a map object or sequence. Then we make it a list, and then that's about the main procedure. Then what we're going to return is nothing but the orange. So this is the corresponding image. So this is the utility function, right? So here we are making the recursive call. So now let's look at the problem logic. So for the problem logic, so what we need to do is just return, right? So we're going to return DFS, the node, if node. Otherwise, so we're going to return null, right? So basically this is a solution format to this problem. So before we make any comments, let's first do a check. So we have changed this one to be version v1, right? Now let's check this one. Yeah, it passes a special case. Now let's look at the generic case. Yeah, it passes all the cases. So here, let me make some comments, right? So basically, in this recursive call, we have hidden the base case for the recursion as here. So basically, if the original node already in D, right? So we just return D orange. So this is the base case, and then we make an instantiation of the image of the original node, and then we make recursive call, right? This is another ingredient of recursion, right? This is the base case, this is the recursive call, and then we're going to the more we do this, we're more towards the base case. So that's the logic here. And this line of code here, basically we can here we can use some unpacking, right, to make it a list. So let's check here. So here I think we need to make a list of the items. So this will also do the job. Let's see. Yeah. But essentially this is nothing but, let me comment to make put the choice, another choice. Here this part is the list. Right. They're the same thing. But personally I will prefer this one because it's more more common or common to more people. So now let's do a final check. Yeah, with that said, basically that's about it for this video. Let me give a quick summary. In this video, we explained two solutions. So basically, these two solutions covers iterative and recursive breadth first search and depth first search, right? To be more clear, for the recursive one, we used the depth first based solution. With that said, that's about it. Thank you.